Hello, everyone. My name is Pritha Srivastava. I am with the Ceph RGW team at IBM. And today I'll be presenting a talk on an upcoming feature in RGW, which is the D4N cache. So here's the agenda for today. I'll briefly introduce what D4N is and give a background about the research project that D4N is about. And later, my talk will mostly focus on the upstreaming effort that has been ongoing to upstream D4N in Ceph. I'll focus on the read cache and the write-back cache that has been implemented so far. And later, I'll move on to discussing the ongoing and the future work that's left as part of the D4N project. And in the end, we'll see a few applications where this D4N cache can be put into use. So D4N stands for Directory-Based Data Center Data Delivery Network. It is a successor to the D3N cache that we already have in RGW. The D4N cache has been designed to be closer to the storage or the data lake so that the data that is cached can be shared amongst multiple applications. It is elastic in nature. And the most important aspect of D4N is that it is based on a distributed directory, which is responsible for maintaining the global state of the entire D4N cache. So D4N is a research collaboration between the MOC students at the Boston University and the Ceph RGW team at Red Hat, which is now IBM. And it is based on the PhD dissertation of Emin Kenar. And there's another interesting PhD dissertation called the Caris Prefetcher, which is by Mania Abdi, which I'll be discussing in one of the slides later. So a few important and interesting design goals of the MOC researchers were to, obviously, provide workload acceleration for generic S3 workloads. And another interesting feature was to come up with an intelligent prefetcher, which is called the Caris prefetcher. So what it does is it analyzes the DAGs of the workload plan query, and then it prefetches objects from the backend into the cache even before the query is executed. So this makes the cache highly efficient and intelligent. Other two interesting features about this project were related to the write-back cache, where they explored storing ephemeral data in the cache and just getting rid of it when the application no longer needs it without transitioning these data back to the backend store. And another one was object packing, wherein they pack small-sized objects into a large one before writing it back to the backend store. So now coming to the upstreaming effort, Amin and Sumatra and another student called Sina, they've been mostly involved from the MOC side. And Samara and I have been working from the IBM side to get things upstreamed. Recently, Gal and Mark Kogan of the RGW team have also started helping us out in the upstreaming efforts. So the D4N code is out there by the students. They have the results also out there. But a lot of it has to be rewritten so that it fits into the current architecture of RGW. So the cache is based on the Zipper API, which is highly extensible and composable, and is separated into 4 drivers: the filter driver, the policy driver, the directory driver, and the cache backend driver. So the cache backend driver serves as an abstraction for multiple kinds of cache backends that we can have in the system. Currently, we provide an SSD-backed cache backend and a Redis-based cache backend. We can also provide implementation for many other cache backends and plug into the D4N project and experiment with them. Similarly, we have a very flexible cache replacement policy. We have support for LRU and LFU DA cache replacement policy at present, but again, we can implement other policies also and experiment with them. We have the directory driver that abstracts away the directory in this case. So the directory is based on the Redis server. As of now, since the Redis open source license has changed, we've shifted to Valkey. Valkey is a fork of the open source Redis project. So in our testing and development efforts, we've been using Valkey in the D4N project currently. And apart from that, we have the filter driver. So the filter driver is a layer between the RGW ops layer and the backend store, which is responsible for intercepting any incoming S3 request and then looking it up in the cache and serving data accordingly. So like other parts of RGW, the cache also uses Boost Azure for its I/O operations. And like I said before, we are using the Redis server for caching all the global state, the location information of the objects, etc. Here is the diagram of a single node cache. We can see the filter layer, which consists of all the 4 drivers that I spoke about. And then we have the backend store and the local SSD in the system. So let's say if we get a GET request for a read cache, the filter driver is going to look the object up using the directory driver and the policy driver and get the object from the cache driver if it is cached. If not, it is going to the backend store. It will get it from there, return it to the end user, and later store it in the cache as well. So next, I'll be discussing a bit about the high-level design of the D4N cache. So the D4N cache is block-based. We have head blocks and we have data blocks. The head blocks saves the extended attributes, and the data blocks store the data. And then in the directory, we have information about all the blocks, like the version information. So the version information is important for us because that helps us in distinguishing between which version is stale and which is the latest version. And then we have the offset size and the host list, which tells us which host caches a particular block. So at present, D4N project uses the LFUDA cache admission and replacement policy. And cache coherence in case of D4N is maintained by probing the directory to get the latest version. So the directory is responsible for saving the latest version of an object in almost all the cases. There is an exception, which I'll be talking about in the coming slides. And the way in which the blocks are laid out in the cache are completely agnostic of the backend store. It doesn't depend on whether we are using a Rados cluster or a DB store cluster. The cache has its own block layout. And as far as deletion goes, even the cache supports lazy deletion of blocks. If we get a delete request, we do not delete the object at once. We perform the deletion at a later point of time. The cache already has support for version as well as for non-version buckets. And we've also provided support for restoring the internal data structures of the cache based on the blocks that are written into the cache in case RGW goes down and has to be restarted. So the way the data has been organized in the cache is in the bucket ID, the object name, and the version hierarchy. And like I said before, version is very important for us. Even in case of non-version buckets, we maintain versioning so that when we get a request, very simple GET request, we know which version we need to serve to the end user, and we do not end up serving stale data to the end user. So moving on to the read cache, when we turn on the RGW filter and set it to D4N, the read cache gets enabled by default. And we do not enable the write cache in that case. We set it to false. And in case of a read cache, we always cache the head block during a write operation. So this is how we always maintain the latest version of an object in the directory. And the data blocks are only cached in case there is a read request for them. In case of version buckets, It is slightly different here. We do not save the latest version in the directory, but in case of a GET request, we always fetch the latest version from the backend store, and then get the blocks from the cache and serve it to the end user. So we've done it this way because we found that there are multiple complexities in maintaining versions in the backend store first, and then the order of versions in the Redis, and then maintaining the consistency between the two when we get a delete operation, and then we need to promote one of the versions to the latest one. So we decided to keep it simple as of now and get the version from the backend store and serve the object from the cache, if it is there in the cache. So objects that are written to the read cache are clean blocks, and they are marked for deletion during a delete request. And later, they can be deleted during the eviction process when they've not been read frequently enough. And if we get a simple GET request, we just look it up in the block directory. We serve it to the end user if it's there. If it's not there, we get it from the backend store and save it in the cache. So for unversioned buckets, we derive the version of the blocks based on an attribute in the backend store, so that we are always serving the latest version to the end user. So now moving on to the write-back cache. The write-back cache can be enabled by turning the config option D4N write cache enable to true. In case of a write-back cache, we cache the head as well as the data blocks during a write operation. For the time being, we are not caching data blocks for multi-part objects. We do it only for single-part objects. And data that are written to the write-back cache are marked dirty. And the dirty blocks of an object are written to the backend store by a cleaning thread after a certain interval of time once they are created in the cache. So the dirty blocks are not eligible for eviction since they haven't been written to the backend store. And when we get a delete request for a dirty block, we do not delete it upfront in the cache also. We mark it as invalid, and later when the cleaning process kicks in, we see that the block is invalid. We don't write it to the backend store, and we delete it from the cache also. And when they are actually written to the backend store, they become clean, and then they become eligible for eviction. In case of version buckets, we maintain the order of the versions in a particular data structure called ordered set in Redis. It's a bit different from the Rados construct here, because Rados, everything is ordered. But in Redis, things are unordered, so we had to use a secondary index to maintain the versions and then have the hash entries as well and work with these two data structures for version buckets. And when we are transitioning objects from the cache to the backend store, we always do that in the order of the creation time. That includes the delete markers also, and we've done a bit of testing around all these things, and things seem to be working fine. So like I said before, the directory is responsible for maintaining the latest version, and this is for versioned as well as for non-versioned buckets in case of a write-back cache. If we get a simple GET request for an object, it will only check the cache for the existence of the block. If it's not there, we'll send back an error. So now moving on to the upstreaming status of the D4N project. The current status is that we're trying to incrementally upstream parts of the D4N code. So early this year, we have merged an experimental version of the read-only cache, which is based on the SSD-backed cache backend and LFUDA cache replacement algorithm. So this did not include the caching of head objects. It only had the caching of tail objects in place. And with the write-back cache, we introduced the caching of head objects also. And currently, we are working towards getting the single node write-back cache also upstream so that it's available in the upcoming release. We have a lot of work ongoing in parallel. One is with respect to the distributed version, where we finally want to have everything working in a distributed fashion. We are also working on cache partitioning. And a lot of testing is ongoing currently. We've written unit tests, we've written integration tests, and we've also started some amount of workload testing on these single node read and write back cache to see how they perform, and if there are bugs, we catch them early on and fix them. So far, the main challenges that we've encountered are mostly related to Azure. So there were some Azure bugs that we encountered in the RGW code. And we also came across some bugs in the Boost Redis client that we've been using to talk to the Redis server, which held us up for quite some time, but then we figured out the solution for that. So coming to the use cases of D4N, D4N can be used in analytical frameworks like Hadoop, etc., to speed up their workloads. And then we can also use D4N for our generic S3 workload acceleration. In case of S3 select, we have different file formats like Parquet, and there's an upcoming work around Arrowflight and Arrow. So D4N can be, based on the internal structure of these file formats, the D4N cache can be made to cache parts of the objects, which will help in accelerating S3 select queries. So we can implement policies which will enable the end user to selectively cache parts of the object. Like, let's say the user can choose to cache only the head block and not the data blocks. Or the user can completely disable caching of multi-part objects and just have single-part objects in the cache. So these are the use cases where we can use D4N. This slide shows the research contributions of people with respect to D3N, the D4N, and the Caris prefetcher. And here we see all the people who've been involved in the D4N project right from the beginning till now. So this brings me to the end of my talk. Thank you. Any questions?
You mentioned single node cache. What's the difference between this one and D3N?
Yeah, so far, D3N didn't have the ability to cache head blocks. It only cached data blocks, and that was mostly caching the RADOS blocks. And D4N has the ability to cache head blocks now. And in the future, it will be a distributed version. D3N is still a single node cache, at least in the upstream Ceph. I can't hear you properly. OK, so here again, we have the directory which is distributed. So whatever is stored in the directory will be visible to all the RGWs here. We are using, eventually, we'll be using a Redis cluster for this, which will cache objects based on consistent hashing. Yes?
Do you also consider to have a Ceph backend for the cache, so you can have
Actually, yeah, the D4N project, the research project did it that way. They had the Ceph backend as the cache and a remote S3 cluster as the backend store. So we haven't considered that as yet, but that could be a possibility in the future. The research did it that way. They had the Ceph cluster as the cache and a remote S3 cluster as the backend store. Yes?
how cache coherence is controlled? For example, are there any
So the directory here is distributed. It's based on Redis. We'll be having a Redis cluster. And since we are storing the head block in the directory, the latest version, so whenever we get a read request for any object, the directory will be aware of the latest version, and that's how we'll be maintaining the cache coherence here.
Is directory essentially a service which is co-located with RGW and then you are
It is, uh, later it won't be co-located with RGW, it will be a Redis cluster.
so then your entry point would your end users would still query your RGW or they would actually first
No, we'll query RGW first. RGW will query Redis and get back information from there. Yeah, I think we're done. Thank you.